Good morning, everyone. We are the Group 3, and our topic for this presentation is all about the dielectrics. By the end of this section, you will be able to describe the action of a capacitor and define capacitance, and explain parallel plate capacitors and their capacitance. Discuss the process of increasing the capacitance of a dielectric, and determine the capacitance given by charge and voltage.
Hi, I'm Janelle Angel Arpancito, and I'm going to discuss to you what are dielectric materials and what does the word dielectric means. Well, get ready to find out. Let's look at the words itself. Dielectric. The word is constructed from the Greek word dia, that means passing through, and electric, that refers to electric fields, giving you dielectric. This term was proposed by a scientist and philosopher from the 19th century, William Whewell. Dielectric was difficult to spell, so with time, naturally, it compressed into the word dielectric. This etymology suggests that a dielectric material is a material that allows electric fields to pass through it. So, dielectrics are non-conducting substances which are the insulating materials and are bad conductor of electric current. Dielectric materials can be made to hold an electrostatic charge while dissipating minimal energy in the form of heat. Examples are mica, plastics, glass, porcelain, and various metal oxides, and even dry air is also example of dielectrics. Dielectric materials are essential in the technologies we are using every day. For examples, they are used for energy storage in capacitors and to enhance devices based on semiconductors. In other words, modern society would not even exist without dielectric materials.
Capacitor. A capacitor is a device used to store electric charge. Capacitors have applications ranging from filtering static out of radio reception to energy storage in heart defibrillators. A capacitor is an electronic component designed to store electric charge. Its applications vary widely from filtering static in radios to playing a crucial role in energy storage for devices like heart defibrillators. So the amount of charge a capacitor can store. The amount of charge a capacitor can store depends on two major factors: the voltage applied and the capacitor's physical characteristics such as its size. The amount of charge or the Q a capacitor can store is influenced by both the voltage applied across its thermal and its physical attributes, like size and capacitance. Higher voltage or increased capacitance allows a capacitor to store more charges, like following the relationship of Q is equals to C times the V, where Q is a charge, C is the capacitance, and V is the voltage. Electric field lines in this parallel plate capacitor. As always, start on positive charges, the end on negative charges. Since the electric field strength is proportional to the density of field lines, it is also proportional to the amount of charge on the capacitors. So, like in a parallel plate capacitor, electric field lines start on positive charges and end on negative charges, depicting the directions of the electric field between the plates. So the electric field strength is proportional to the density of these field lines, and it correlates with the amount of charge on the capacitors. So for example, if you increase the charge of the capacitor plates while keeping other factors constant, the electric field strength between the plates will also increase. So this demonstrates that the direct proportionality between the amount of charge and the electric field strength in a parallel plate capacitor.
The electric field is proportional to the charge, where this symbol means proportional to from the discussion in electric potential in a uniform electric field. We know that the voltage across parallel plates is voltage is equal to electric field and distance. Thus, voltage is proportional to electric field. It follows then that voltage is proportional to the charge, and conversely, charge is proportional to the voltage. This is true in general. The greater the voltage applied to any capacitor, the greater the charge stored in it. Different capacitors will store different amounts of charge for the same applied voltage, depending on their physical characteristics. We define the capacitance to be that the charge stored in the capacitor is proportional to capacitance. The charge stored in a capacitor is given by charge is equal to capacitance and voltage. This equation expresses the two major factors affecting the amount of charge stored. Those factors are the physical characteristics of the capacitor and the voltage. Rearranging the equation, we see that capacitance is the amount of charge stored per voltage, or capacitance is equal to charge over voltage.
So let's move on to capacitance. What is capacitance? Capacitance, or C, is amount of charge per volt, or C equals BQ. The unit of capacitance is farad, or F, named of Michael Faraday in 1791 to 1867. An English scientist who contributed to the field of electromagnetism and electrochemistry. Since capacitance is a charge per unit voltage, see that a farad is a coulomb per volt, or 1F equals 1C over 1V, or it's read as 1 farad equals 1 coulomb over 1 volt. 1 farad capacitors will be able to store 1 coulomb, a very large amount of charge, the application of only 1 volt. 1 farad is thus a very large capacitors. Typically, capacitors range from fractions of a picofarad, sample of PF equals 10 minus 12 F, or it's read as 1 picofarads equals 10 minus 12 farad. To millifarads, example of 1 mF equals 10 minus 3 F, or it's read as 1 millifarads equals 10 minus 3 farads. It shows some capacitors. Capacitors are primarily made of ceramic, glass, or plastic, and it depends on purpose and size. Insulating materials is called DIELECTRICS, and it's commonly used in construction, and it will be discussed after this.
So hello everyone, I'm Aralua and I'm here to talk or to tell you the formula of getting the capacitance of a parallel plate capacitor. So as you can see at our presentation, we have there the formula. The formula is C is equal to epsilon naught A over D. So the formula that is provided at our presentation, that is the capacitance of a parallel capacitor, wherein the letter C is the capacitance and the EO, or what you see there, is the vacuum informativity constant, that is also known as epsilon naught, that is approximately 8.85 times 10 raised to the power of negative 12 F over M. The letter A is the area of one plate in square meters, and the letter D is the distance between the plates in meters. So, this formula essentially tells us the capacitance of a parallel plate capacitor is directly proportional to the plate's area, or the letter A, and inversely proportional to the distance between the plates, or the letter D. The constants of epsilon naught reflects to the permittivity of the space between the plates, which is a physical constant. So in this slide, we have a example capacitance and charge stored in a parallel capacitor. So as you can see, we have direct questions, or two questions to be exact. And I am here now to solve it with you and to teach you how to solve it correctly. So, the number one, the question is, what is the capacitance of a parallel plate capacitor with metal plates, each of area 1.00 meter squared, separated by 1.00 millimeter? So, now, what we are going to find? Yes, the capacitance. What is the capacitance? So, now we're going to use the formula of capacitance. The C is equal to epsilon naught A over D. So, the first procedure to move on or to is given muna. So, the given there is A is equal to 1.00 meters squared. The D is equal to 1.00 millimeter, or if we convert it into meter, that would be 0.001 meter. And the epsilon naught, it is 8.85 times 10 raised to the power of negative 12 F over M. So now we're going to plugging in the values. So this would be look like C is equal to 8.85 times 10 raised to the power of negative 12 F over M multiplied by 1.00 meter squared over 0.001 meter. So now we're going to calculate it. So if we're going to calculate it, the answer, or the answer that we will get or will be getting, is 8.85 times 10 raised to the power of negative 9 F. So, therefore, the capacitance of the parallel plate capacitor is 8.85 times 10 raised to the power of negative 9 F. So, let's move on to number 2. The question is, what charge is stored in the capacitor if a voltage of 3.00 times 10 raised to the power of 3V is applied to it? So in this equation, we're going to use the formula of Q is equal to CV. So the given is, or the given are, V is equal to 3.00 times 10 raised to the power of 3V, and the C, or the capacitance, is 8.85 times 10 raised to the power of negative 9F. So now we're going to plug in the values. So this would be look like in Q is equal to 8.85 times 10 raised to the power of negative 9F multiplied by 3.00 times 10 raised to the power of 3V. If we're going to calculate, we'll be getting a Q is equal to 2.66 times 10 raised to the power of negative 5C. So therefore, the charge stored in the capacitor is 2.66 times 10 raised to the power of negative 5C. And I hope you guys get a lot of my explanation, or yeah. That's all. Thank you.
So that's all. Thank you for listening and watching here in our video. Hope you learned something about what we have discussed to you all. Thank you.